So now I want to go through and actually find some examples of computing. I want to actually compute some examples of residues. And I want to compute the residue of a function f at the value z0, where I'm going to give you f and z0. So let's start with f being e to the z minus 1 over sine of z, and z0 being 0. So I want to compute that residue first. And as you might notice, what's going to happen here is that you actually have a removable discontinuity, because if you look at e to the z minus 1 over sine of z, this limit is going to turn out to be 1. And so the limit as z approaches 0, I should say, so z naught is now 0. But the limit as z approaches 0 of e to the z minus 1 over sine is just going to be 1, because you can do it a number of ways, the L'Hopital's rule or Taylor's theorem. So e to the z minus 1 has just a z term. So it's e to the z minus 1 is z plus 1/2 z squared plus 1/6 z cubed and so on. Sine of z, we know the Taylor series expansion, but it starts with z and then it has a z cubed term and a z to the 5th term, and you can factor z out. So those both end up canceling, and you end up with a removable discontinuity, and therefore the residue. So the residue is 0, because you have a removable discontinuity there. All right, so next let's look at the function e to the z, 1 over e to the z minus 1, and we're going to again calculate the residue at 0. Now here, it's not removable, because if you look at e to the z minus 1, that's going to be z plus 1/2 z squared and so on, and you're going to have a problem at 0. But it turns out that all you have to do is multiply by z, and what's going to happen is you're going to get the limit of z over e to the z minus 1. That's going to exist and not be equal to 0, and therefore this is a pole of order 1. And if we have a pole of order k from the 5th rule that we talked about in the previous video, if we have a pole of order k, we know how to handle that. So that tells us that our residue of f at 0 is going to be the limit as z approaches, in this case, 0, of z times f of z. So it's going to be this limit of z times f of z, and that's going to end up being, in this case, 1. This actually is also, so I just applied rule 5 without really thinking about it. That is also rule 2 that we talked about. So if you have z minus z naught times f, and if that limit exists and equals some non-zero number, then that non-zero number is the residue. That's exactly what just happened here. Okay, so you can think about this either way. Let's look at z plus 2 over z squared minus 2z. And again, I want to look at the value being at 0. Okay, and so when I think about what's going to happen here, and so you can think of this as however you really want to think about it. You could think of this as rule 4 or rule 5, but here you have g, where g of 0 is non-zero, and h, where h of 0 is 0, but the derivative is 2 minus z, and at 0 that's 2, not 0. So you can kind of use either formula you want to use, but I still like to use the fact, so what I just said emphasizes that this is a simple pole, and you can do that also just by factoring, right? Z plus 2 over z squared minus 2z is equal to z plus 2 times z minus 2. And so here's your g and here's your h. And with the h, you factored out one of the zeros. It's to the first order, so that's what makes it simple, is that our function has a pole of order 1. So again, lots of ways that you can do this, but my favorite is just to compute phi, and then take the k minus first derivative. Here our k is 1, so we're going to take the 0th derivative and think about what happens to this function as we approach 0. So this is going to be the limit of, as z approaches 0, of z times our function. So z times z plus 2 over z times z minus 2. And the z's cancel, and we end up with 2 over negative 2, which is negative 1. So here our residue is going to be negative 1. Our fourth example, I think I just switched to whatever, Arabic numbers instead of Roman numerals, but that's fine. So our fourth function is 1 plus e to the z over z to the fourth. And again, there's a few ways that you can compute the residue here. One way, just because I think it's easiest, is you can actually just compute the Taylor series for e to the z. And so this is going to be 1 over z to the fourth times 1 plus the Taylor series for e to the z, being 1 plus z plus 1/2 z squared plus 1/6 z cubed, and so on. And so this tells you that this is going to have 2 over z to the fourth plus 1 over z cubed plus z squared over 2z to the fourth. So a better way to write that would be 1 over z squared with that 1/2 coefficient down there, plus 1 over 6z plus 1 over 24, and so on. And so, of course, your residue is going to be this 1/6. So the residue is 1/6. So in this case, actually calculating the Laurent series was easy. If you wanted to do this the other way, notice that z to the fourth is the smallest term that you can multiply by, so that this term is non-zero. So notice that here our k is equal to 4. So we have a pole of order 4, which we already knew because we have a pole of order 4. And therefore, we can look at the limit as z approaches, in our case, 0, of the third derivative at z over 3 factorial. And so now we just need to think about what's the third derivative of phi, where phi is equal to z to the fourth times f, which is e to the fourth times 1 plus e to the z over z to the fourth, which is just 1 plus e to the z. And so, of course, the third derivative, the first derivative is e to the z, and therefore the second and third derivative is also going to be e to the z. And so that tells you that the third derivative evaluated at 0 is just 1, and therefore we end up with 1 over 3 factorial, or 1/6. So either way you want to compute this, the residue is going to be 1/6. So that's that. Example number 5. So example number 5, we have the function e to the z squared over z minus 1. And here we want to compute the residue at 1. Now, I have the formula for e to the z memorized if we differentiate at it's centered at 0, I mean, not centered at 1. And nothing really changes if it's just e to the z. But if it's e to the z squared, then when you're starting to plug in values, you're going to have kind of a crazy formula there. So rather than worry about all of that, let's just go back and think about how we computed residues based in the last video. And this is going to be a pole of order 1, because here we have a function, we can call this g, where g is non-zero when we plug in 1. And then this is h, where h of 1 is 0, but h prime of 1 is non-zero. And so lots of ways that you can do this, but again, I just like to take the limit as, in this case, z approaches 1 of z minus 1 times f of z. And that's going to be the limit as z approaches 1 of e to the z squared. So that's just going to be e. And then as our last example of computing residues, let's look at e to the z squared over z minus 1 squared, where we're going to look at the residue of that function at 1. And here this is going to be a pole of order 2, so our k is 2, and therefore the residue of f at 1 is going to be equal to the limit as z approaches 1 of the first derivative of phi, so the derivative of phi, where phi is just going to be e to the z squared, because I'm multiplying by z minus 1 squared. So in this case, it happens to be just the numerator. In general, it'll be more complicated, but in this case, it's just the numerator, because the only thing that we're dividing down by here is the other thing. So this is just going to be phi prime of z, So this is going to end up being, let's see, what's the derivative of e to the z squared? It's going to be the limit. So it's going to be, let's see, 2z e to the z squared plus, no, not plus anything. That's it. So it's going to be 2z e to the z squared. We're going to plug in z equals 1, and we end up with 2e. Okay, so there's our residue there. You can also think of this as rule 3 that we had, where you have g of z over z minus z naught squared. That's literally what this is. And then you take the derivative of the numerator, plug in this case, z naught is 1, so you plug in 1, and then we end up with 2e. Okay, so again, either way we want to do this, we end up with the same value for the residue.